Hey everybody. So today we're going to talk about, well, in this part of the lecture that is, we're going to talk about other planetary systems. So when I was growing up, nobody knew if there were any other planets around any other suns, right? Of course, we know that all the other stars are other suns, but whether they had planets or not was a big mystery. No one knew. We thought, well, they probably do, but maybe planets were rare. Maybe we, with our, 8 planets, 8.5, I suppose, maybe we're just weird, right? Maybe we were the only ones, or one of very, very few, like one in a million or one in a billion. We had no idea. And then in 1995, we discovered the very first exoplanet, and from then on, it's been exoplanet crazy. We have thousands of detected exoplanets, and we think that most stars have at least one planet. So it's a big shift in what we think, and we now know that planetary systems aren't rare, which is a really amazing thing, because of course this relates to, is there life in the universe? If planetary systems were really rare, one in a billion, so if one in a billion stars had planetary systems, then it's unlikely that there was life in the universe besides us, right? Or because we don't really know what the probability of having life on a planet is if you have a planet, right? And we'll talk about all those factors a little bit more later. But now that we know that they're not rare, that makes a whole different thing. And then the whole issue in planetary detection is, of course, trying to find planets that are the right distance away from their stars and orbiting the right kind of stars to maybe harbor life. So we'll talk about that too. So let's try to understand how we look for other planets. All right. Well, first of all, why didn't we detect them till 1995? Well, it's super hard. There is a big brightness difference between a sun, like a sun-like star, right? Very bright, about 1 billion times brighter than the light reflected from its planet. So you can't just point a telescope. In general, you can't point a telescope at and just detect a planet. And here's a nice analogy using our 1 to 10 billion scale that we used before for looking at things in the solar system. This is like being in San Francisco and trying to see a pinhead, right, very small, 15 meters from a grapefruit in Washington, D.C. Remember, our pinhead or our ballpoint point was the size of the Earth, right? If the sun was the size of a large grapefruit. So this is that same scale. So imagine being in San Francisco, even if the Earth were flat and you could look straight across, right? Very, very, very difficult. And then on top of that, imagine the grapefruit is 1 billion times brighter than the pinhead. Okay, so super difficult thing to do. But there's many ways that we can and have found exoplanets, and we'll talk about that. Okay, so how do we do this? Well, there are kind of two ways. There's direct, and believe it or not, this is the same idea of, looking for the pinhead, get a big telescope, look for the pinhead, right? Direct measurements where you basically take pictures and get the spectra, either the spectra of the planets themselves or a picture of the planet themselves. We'll talk about that. That's a tough way to do it, but we have done that. That wasn't the first way the planet was detected, but we have been able to do that here and there. And indirect, that's much more common. This is measures of stellar properties that reveal the effects of the orbiting planet, and we'll talk about all those. Okay, so first, there's this idea that the planets are tugging on the star. So both the planet and the star are actually not, for instance, Jupiter is not just orbiting the sun. In fact, the sun and Jupiter orbit around the common center of mass. And so that causes this sort of wobbling of the sun. And let's take a look at that. So here's a little simulation, and here's the sun just sort of sitting here. And I'm going to show you the simulation in a second. I'm going to turn on all the planets in a second. I'm going to go to the center of mass here and just show you. So here's the two masses of two things orbiting each other. And in fact, so you might think, well, the little guy is just going to orbit the big guy. But in fact, the center of mass is here at this cross, and they both orbit that point, Okay, that's the center of mass. And that's true for our sun too. So let's take a look at what that looks like. So first, I'm going to turn on Earth. Okay, well, how about if let me just reset everything. We'll start time over. And look, this is going very fast, right? It's about 1,000 days per second in this animation. I can make it go faster. But the Earth isn't really tugging much on the sun, right? The Earth is much, much, much smaller than the sun, and so it doesn't tug a lot. But how about if we put in Jupiter and see what happens? So look where the center of mass has moved to, right? And now the sun is going around that center of mass because Jupiter is tugging on it. How about if we add in some other big things like Saturn? Yep, so that changed it as well. And how about all the others? We'll just add all the others in now. Everybody come to the party. Okay, so you can see the sun is actually doing this crazy little motion. Now it takes many, many years to watch this go, these motions, but it certainly isn't just the planets orbiting the sun. The sun is actually moving because it's getting tugged by all the other planets because both the sun and the planets orbit the center of mass of the solar system. That's what they do. So let me show you a picture of that. So here we have sort of the motion of the sun, and you can see it's from 1965 all the way through, this is predicted, 2020, and you can see the sun is sort of wobbling around, right? So if you were around another star and you were measuring the motion of the sun, you could determine the masses and orbits of all the planets because you would say, oh, look, that sun is wobbling. It must be getting tugged by all the planets around it. And so that's a big way that we find exoplanets. Now, again, this is called an astrometric technique. And these motions are difficult to measure if your sun is the thing you're trying to detect is far away. So, for instance, if you were looking from 30 light years away, so let's say you're observing the sun from a solar system, from a system out there, a planet, an alien planet that's 30 light years away from the sun, the change in this wobble, right? So the length of the wobble would be roughly what? 0.0010, right? So let's say twice from here to here, twice this distance here. This is a little distance scale. That's 0.0005 arc seconds. So it would be something like 0.0010. So twice of that, right? Arc seconds. That's a tiny, tiny motion. So you have to be pretty good at your astronomy to be able to detect that. All right. So there's another way that we do that, and that is with Doppler techniques. And so what happens here is that you have the orbit of sort of an unseen planet, and it is causing the wobble, right? So you're not directly looking for that change between the two sides of the wobble, right? Like we were just looking on that diagram. You're now looking at Doppler effect, right? Because the sun is going in this extrasolar system, right? The star is going towards us and then away from us and towards us and then away from us because it's being tugged by its unseen planet, right? So here's a little diagram of that. As it's going towards us, of course, we get a blue shift. As it's going away from us, we get a red shift. Now, current techniques can measure the motions as small as 1 meter per second, which is walking speed. That's quite amazing. So we can use the Doppler effect to measure this wobble instead of a direct measurement of the wobble, right? Okay. Okay, so the first exoplanet that was discovered was 51 Pegasi, and it was indirectly revealed, right, by sort of the radial velocity. Again, this is the Doppler effect, right? Now, it has a period of 4 days, which is really quite amazing. So that means it's very, very close in to its sun, right? Remember, that's Kepler's third law. The shorter orbital period means you're closer to your star. So here is an artist's conception of that. This planet orbits at about a 0.05 AUs from its sun, and it's about half the mass of Jupiter, so very big planet, whipping around every 4.2 roughly days. So quite an amazing thing. Now again, I hope that you got the point that if you have a bigger planet, right, you cause more wobble. And so it's easier to detect bigger planets, the wobble of the suns of bigger planets, right? So that's why a lot of what we've discovered, as you'll see, are these big, big planets. And the goal of getting Earth-sized planets, trying to figure out where they are and which suns have those planets is tough because they don't cause much wobble, as you saw in that simulation. So the cool thing about Doppler shift data is that it can tell us about the planet's mass, okay, which is why we know what the mass of 51 Pegasi was, and the eccentricity of the orbit. Remember, that tells you how elliptical it is. So we can get both of those from Doppler shift data. Now, but the problem is we can't get exact mass measurements for planets without knowing the tilt of the orbit in Doppler shift. So we can get a lower limit on masses. So I have to caveat what I just said, because if your orbit is not right, if you don't know the tilt of the orbit, in other words, you could have an orbit that's you're right edge on the orbit, right? And then the velocity that you see coming towards you is the full velocity of the star. But imagine you're tilted this way, that's not going to be the case. It's only the component that's coming towards you that's going to give you that blue shift or red shift. And if we don't know the tilt, which we have no way of knowing, then we really can't estimate the mass. We can make a lower limit on the mass. And so that's what we always have to think about when we're saying what the mass of an extrasolar planet is. All right, so there's another way that's called a transit, or you could call it an eclipse if you like, and that's when a planet goes in front of its sun. Again, we have to be at least somewhat edge on to the orbit. So, right, so imagine if you're looking down on the orbit, so let's put the orbit in this plane, looking down on the orbit, you see this, if you were next to it, you could see the planet going around the sun, but you're not going to see an eclipse, right? You're never going to see the planet block the light of the sun because you're sort of looking down on it, on the orbit. So you're not going to see an eclipse or a transit in that case. So we have to be lucky and be seeing these things at least somewhat edge on. Okay, so let's look at a simulation of that. Okay, so here is a little simulator that shows you an eclipsing planet. So here's the sun, here's a planet, and you can pick from some of the known exoplanets. Okay, so I just picked this XO1b. Now, so if we look at the inclination, so the inclination of the orbit, if it was 90 degrees, we'd be full edge on. You can kind of see that we're not full edge on, right? But as this planet goes forward, I can't drag it, I can drag this thing though. I'll tell you in a second what this is. So as the planet sort of goes around its sun, it's going to come in front of the sun. It's going to block some of the light that comes from that sun, right, from that star. So if we watch the light curve, here's the curve where it's not blocking, right? You can see it's outside. But as I move this line, you can see, look at the planet. Okay, so now it starts to come in and the light starts to dim, right? Because we got a little bit of the planet is covering the sun or the star. And then the planet is fully in front of the star, and so it blocks in the same amount. It blocks all the way until it starts to leave that eclipse, right? And we get more and more and more light as it leaves, and then we go back to our regular not having it in front of the star at all. So we can detect these dips from these eclipses, but of course only if the inclination is the right inclination. So I can change that here. Let's go to an inclination of 80, right? And now you're at the wrong inclination. You're never going to see an eclipse, all right? So you have to have the right inclination. You just got to be lucky. Got to be, lucky that we're looking at the right inclination to see this. And that's true for a lot of the detection methods. So if the detection method of the Doppler shift depends on that, the detection using these eclipses depends on that. And then the direct method doesn't, which is nice. And we're going to see another method that doesn't really depend on that as well. Okay, so another thing that's really cool is we can see a change in the spectrum when we see these eclipses, sometimes. So imagine you've got a planet here and it's about to cross in front, right? You of course see a spectrum. Remember, we see this spectrum of light, usually a dark line absorption spectrum represented by these two little dips in light. Of course, it's much more complicated than that in general, but just, right, think about the two little dips in light. And now, if you see the planet in front, right, the light has to go through the atmosphere of the planet. So you could pick up other little dips. They really should have drawn these in different places, these little dips, right, because there's probably different elements in the atmosphere of this planet. But you could see the atmosphere in the planet through its spectra, sometimes through these eclipses. So that's very exciting because you could detect if there's water vapor in the atmosphere, oxygen in the atmosphere of these exoplanets. So very, very exciting thing to do here. Okay. You can also figure out the temperature map. So this is sort of, imagine taking the planet and just unfurling it or uncurling it, right? So and to make this little map, and you can see this is the center of the day side of the temperature, right? Here, and the center of the dark side back here. I meant that would be curling it back around and making it into a globe again. But you can get the surface temperatures of the planets from the change in the infrared brightness during an eclipse. So we can get a lot of information from these eclipses. And then there's direct detection, the first one in 2004. And that entails just sort of trying to block out the light of the sun. So remember, the sun is I keep saying suns when I really do mean suns outside of our solar system, right? So I should say stars, but remember they are suns. So you block out the star's light, and you're trying to block enough of the light so you can detect other planets. Okay. And then there's something called gravitational microlensing, which I'm going to show you a little animation for in a second. And this detects the bending of light from a distant star and planet. Okay, you don't have to understand this graph. It's rather complicated, but when you have a background star and then you have a planetary system sort of moving in front of that background star, the gravitation of that moving solar system, right, that moving star with planets, will cause the sort of curving of light due to gravity. Now, we haven't really studied the theory, Einstein's theory of general relativity, which is the newest theory of gravity, and that's been very well tested, that says that mass curves space-time around it. We'll be studying that later. And so light sort of bends around an object, okay? And we can detect very low-mass planets with this technique. So let's go look at an overview of these techniques. So here's a nice overview from NASA. 5 ways to find a planet. Watching for a wobble. So let's take a look at that. So again, right, you're watching for the wobble caused by planets tugging on the star. And you do that by the Doppler effect here. We're getting, so what we have here is a blue shift as the star comes towards us, and a red shift as it goes away. Okay. All right, so let's go to the next one. That is searching for shadows, and this is the eclipse, right? Let's look at multiple planets, and look, we have 2,900 planets were discovered with this method. It's a very effective method. Again, you have to be looking at least a little bit edge on to these orbits, right? So there are probably lots and lots and lots of planets that we can't discover this way, and we can't discover with the Doppler effect, right? So here comes the next one. You see another dip. And the next one, you see another dip, right? So we can detect multiple planets this way, which is really amazing. Okay, let's take a look at the next way. This is that direct imaging. So you blot out the light of the star, and then you can see planets hanging out, right? If you blot that brightness out, you have a much better chance of direct imaging. And but it's hard, and you can see there's only 44 planets have been discovered that way. Okay, so the next method here is this gravitational microlensing. And like I said, we haven't really talked about the fact that mass sort of curves space-time around it. which can make light waves bend. So you see here's a star and its planet sort of causing the light waves from a distant star to bend. And we can detect that little bend in the light. And so we've had about 60 planets discovered, and this is a good way to detect planets that are smaller than these big Jupiter or bigger than Jupiter-sized planets. And then one last method, and you can see only one planet was discovered this way, is literally by looking for those minuscule movements of a star caused by the gravitational tugging. So you're actually looking for the changes in the position of a star. So that's pretty tough, and we've only really seen one planet that was discovered that way. Okay, so what can we learn from all of these different methods besides just detecting the planets? Well, we can figure out their orbital period, the distance, the shape of the orbit, how eccentric it is. We can figure out the planet's mass, or at least a lower bound. Its size, because think about eclipsing planets, you can tell how big they are by how long they take to come out of the eclipse. Their density, the composition even sometimes. Okay, so let's look at some properties that we've seen for planets. And this isn't all the planets that were discovered. Okay, so for instance, most of the detected planets have orbits that are smaller than the orbit of Jupiter. So it's harder to detect when planets are farther out. So most of the planets we've detected have these smaller orbits, smaller than the orbit of Jupiter. And here's sort of a graphic of them. Obviously not all the planets we've discovered. Okay. The orbits of some extrasolar planets are much more elongated. So we see a lot more of high eccentricity in these extrasolar planets. So if you look down here, the planet in our solar system with the highest eccentricity, not including Pluto, is Mercury. But look at all these extrasolar planets with much higher orbital eccentricity, right? So it's kind of amazing that they have, in general, higher eccentricity. And like we saw in the eclipse simulation where you can see multiple planets, we've seen lots of stars with more than one detected planet. So it's very cool, right? So this particular one here, right, you have 2 planets, etc. So there's a lot of we know one, that probably most stars have planets. On 2, and probably most stars have more than one. Okay. So let's just look at the distribution of masses. So here's planet mass in terms of Earth mass. So this is 1 Earth mass. And this is the orbital distance. So here's 1 AU where the Earth is. And in green are the solar system objects. So for instance, here's Earth at 1 AU and 1 Earth mass, right? This is as of 2013. So this graph has changed since then. It's actually quite difficult to find these graphs up to the minute. Graphs where we could see, what's been happening between 2013 and 2018. All right, but you see, like, the different methods, transit, right? The radial velocity, which is basically Doppler effect detection, microlensing, and direct imaging. And you can see the direct imaging really is only good for these really high mass planets. As you could imagine, it's tough to detect them when they're small. Microlensing is starting to get down into that area where we have about Earth distance from the sun and about Earth mass, right? So this right here is 2 Earth masses, 3 Earth masses, so on. And this has changed since then. Okay, so how do these extrasolar planets compare with planets in our solar system? It's a good thing to think about. So some extrasolar planets have these highly elliptical orbits, like we said, and some massive planets called hot Jupiters orbit very close to their stars. In fact, the very first exoplanet that we saw was about half the mass of Jupiter and super close to its star, and so we call those hot Jupiters. And for instance, here you can see sort of a comparison between our Jupiter and a hot Jupiter. So in our Jupiter, look at here, we have 5 AUs from the sun, right? Their composition's the same, hydrogen, helium for both. This one, 0.03 AU, right? So super close, way within the orbit of Mercury. And the orbit's long for Jupiter. It's super short. This thing is whizzing around its star. It's amazing. And it's much hotter because it's so close. So we have a cloud temperature of up to 1300 Kelvin, whereas our Jupiter has about 130 Kelvin cloud temperature. We think that the clouds in these Jupiters have clouds of rock dust, so it's really an interesting object. And these hot Jupiters can be anywhere from 0.2 times the mass of Jupiter to up to 2 times the mass of Jupiter. So imagine something twice the mass of Jupiter, super close to its star, within 0.05 or so AU. It's an amazing thing to think about. And we think that these Jupiters were actually not formed there, but kicked into that orbit by a gravitational encounter of some kind. Okay, so how do we search for Earth-like planets? Well, we have a very important satellite called the Kepler satellite, and it was launched literally just to look for transiting planets. So that's the eclipsing way of detecting extrasolar planets, and it's designed so that it can measure declines in brightness of 0.008%. So that is quite sensitive, and sensitive enough to detect Earth-like planets, Earth-mass planets, when they eclipse their stars. So let's take a look at a little video. Okay, so before we watch the video, I want to just tell you about something called the habitable zone, and you've probably heard of that. And what that is, it's a region of how far away you are from your star, right? So if you're a planet and you're a certain distance away from your star, you could be in the habitable zone, and habitable zone is where you can have liquid water. And there's only a certain region away, you can see it in the green here, from the star that you can be where water can be liquid. Here it's too hot, you're not going to have liquid water, it would just boil away. Here too cold, it would freeze. So it's really important for us to look for these things, because we think that liquid water is very essential, at least as far as we know, for life. So if we could find planets that are roughly kind of rocky planets like the Earth, about the size of the Earth, in the habitable zone, it's a really good indication of possibility of life. Not saying that life exists there, may not, but at least the conditions would be right. And here's a video about Kepler's first discovery of an Earth-sized planet in the habitable zone.
NASA's Kepler mission has discovered the first Earth-sized planet orbiting in the habitable zone of a star outside our solar system. The newly discovered planet is called Kepler 186f and is about 10% larger than Earth.
Kepler 186f is the first validated Earth-sized planet in the habitable zone of its star. It's the outermost of 5 planets to orbit a star that is smaller and cooler than the Sun. This planet orbits its star every 130 days, and so this places it in the habitable zone, where it's in a region where it could have liquid water on its surface.
Kepler 186f resides in the Kepler 186 system, about 500 light-years from Earth in the constellation Cygnus.
This planet, Kepler 186f, orbits a star that's cooler and dimmer than the Sun. So while we may have found a planet that's the same size as Earth and receives a similar amount of energy to what Earth receives, it orbits a very different star. So perhaps instead of an Earth twin, we've discovered an Earth cousin.
On the surface of Kepler 186f, the brightness of its star at high noon is only as bright as our Sun appears to us about an hour before sunset. Scientists believe Kepler 186f is likely to be a rocky world, but are unable to confirm its mass and density.
This is one of the big milestones that we've been looking for in our attempts to find out if there are places just like home and if there's life out there. One of the big steps is to say, is there somewhere that looks, to all intents and purposes, like Earth? Well, we don't know just yet, but we know that there are places that at least look similar.
Managed by NASA's Ames Research Center, the Kepler mission collected this data using a space-based telescope to search one part of the galaxy for potentially habitable planets.
So pretty amazing. Again, we can't confirm its mass yet, but we do think it's a rocky planet. So next time you look up into the sky, look for Cygnus the Swan, which here, and if you find this asterism, remember it's not called a constellation, the picture that people draw out of stars is called an asterism, but this tells you what part of the sky you're looking in, and that's Cygnus. That's the area of the sky. So find Cygnus and think about the fact that you may be looking up into a region of the sky where 500 light years away there may be aliens looking back at you. Okay, so we have another mission to tell you about. Oops, hold on, I gotta go back to our thing. Here we go. And that is Gaia. This is a European mission, and it's really meant to look at stars themselves, but can also measure these precise motions, and it's found a lot of extrasolar planets as well. Okay, so please pause your video and answer the question.